Okay, so like I mentioned earlier, we're going to record this session. I think every week you guys will be the victims of me recording the session. So this is a recording that I'll post on the online class in case somebody is absent or they're taking the online version, they'll have access to it. So if you please join the Paradigm that is on the board and sign into class. We will begin in a few minutes. So the other class, they will have a review day before this. You guys will not have a review day, but you will not have this. Okay, so that's the top class. So you'll notice that your due dates have been delayed one week. That's just for the face-to-face class, not for you guys listening online. Okay, you guys still have the same dates. Okay, I have 7 students connected. I think that I have more than 7 students, so we need some more people connected. You have until the song ends to get connected. I don't know anything about your password, so go do that. Sometimes if you're having trouble joining the internet, you have to reset your password. So, all right, I have 17 students. It's almost the end of the song. I need a few more people. Um, Trick question. In biology, absolutely. Science, absolutely. Physics, yes. But like, you don't have to take physics. Physics is what you make of it. It's mostly math. All right, our song is over. So I have 21 students. Awesome. All right. If you didn't get a chance to join, the code is on the board. It's also in the top right-hand corner. So let's go ahead and get started. As always, we land on this home page. So if you see this home page, you can click on this book. This is our notes. You can print these and take paper notes. It's a great guide to help you stay organized. If you didn't print them, you can click on it and take notes on your computer, so you can edit them on the computer. But it's a useful tool, and if you take notes, there might be an opportunity to turn them in for extra credit. Let's go ahead and get started. Our objectives for today, we are going to learn about matter and the elements. We're going to review the periodic table, which most of us should be pretty familiar with, but we'll review the periodic table. And we're going to learn about interactions between different atoms and how they connect to each other to create molecules. We're also going to talk about water, which is a very interesting molecule, and we have a lot of water in our bodies, so we'll talk about its role in our bodies. All right, First, this is our periodic table. This should be review. We should know what the periodic table looks like. But if you want to know more about the periodic table, you can look into the history of how the periodic table was designed. All these elements are grouped together based on their properties. And it just so happens that their properties line up really well with their structure. So the structure leads to the properties. Element is a pure substance where all the substance has the same characteristics. So if I have a block of gold, everything in that block of gold will have the same number of atoms. Will have the same number of protons, and they will have all the same characteristics. If I cut that gold in half, and I cut it in half again, and I cut it in half again, in infinity times until I get to the very, very, very smallest particle that has the same properties as gold, so an orange, shiny, metallic substance, I would get an atom, which is the very smallest amount of an element I can have and still retain its properties. If I go any smaller than that, I've broken it, and it's not going to have the same properties. The cool thing about elements is that, like I said, they share properties and they're organized in these families. And we'll talk about families next. But for instance, hydrogen, we're going to talk about hydrogen a whole lot. Hydrogen is only one single proton, and it has one electron, and it does some cool things in your body. The other cool element to look at is carbon. Carbon is right here, and carbon is a very light element, meaning it's kind of small, it's high up in the periodic table, but it makes 4 different bonds, which is a lot of bonds. And we'll talk about why carbon makes 4 different bonds in a second, but carbon is known as our organic element. Anything containing carbon is organic, and anything that is alive is going to contain carbon. So we talk about carbon a lot. Carbon, hydrogen, oxygen, and nitrogen make up most of our body weight, and a lot of that is hydrogen and oxygen in the form of H2O, water. We also have other substances in our body that are non-organic, like water is non-organic, salt is non-organic, they don't contain carbon. So we need both. Now, the periodic table is organized in families, in these columns. The rows are called periods, and the columns are called families or groups, and they share characteristics. The neat thing that I think is super cool about the periodic table is I can look at family 1 and I can assume a lot about it just because of its place in the periodic table. Family number 1 only has 1 outside electron, just like hydrogen only has 1 electron. Well, I can go all the way down here and I still only have 1 outside electron. All of these have 1 outside electron, and that outside electron is called a valence electron. That's really important for the properties. Since all of these elements have 1 outside electron, they all share the same properties, such as being a very dull gray metallic. They're kind of soft for a metal, meaning you could probably cut it with a butter knife. It might take some effort, but you can cut it. And they're also very, very reactive. They only have 1 outside electron, which makes them extremely reactive. And they're so reactive that we have to keep sodium inside of oil so that it doesn't react with the water in our atmosphere. Especially here in Southeast Texas, it's very humid. There's lots of water vapor in the air, and it will cause sodium or cesium, any of the things in group 1 to explode when it comes into contact with water. Very reactive. Anything in group 2, the alkali earth metals, they're going to have 2 outside electrons. Now we skip the transition metals because they don't really follow our rules. They do some funky things, and they will have different number of valence electrons, but you can find gold in the transition family, copper, silver, they're all here in the transition metal family. So we jump over to the boron family, and they have 3 outside electrons. Carbon family, we already talked about carbon itself and how it has 4 outside electrons, allowing it to make 4 bonds. Nitrogen family has 5 outside electrons. oxygen family has 6 outside electrons, and the halogen family has 7 outside electrons. So we can look at the periodic table and very easily tell how many outside electrons are available. And the most outside electrons are the ones that determine its properties and its bonds. Most elements want to become stable, and they are most stable when they have 8 outside electrons. So the noble gas family already has 8 outside electrons, and they're pretty non-reactive, not very reactive. Things like neon, radon, argon, these elements, these noble gases, generally don't make bonds because they already have 8 valence electrons. Well, what does that mean for the halogen family? They have 7. Are they going to want to lose 7 electrons, or are they going to want to gain 1 electron? They're going to want to gain 1 electron. And the most common place for halogens to gain 1 electron is by creating an ionic bond with these alkali metals, because they have 1 available outside electron. And this is what we call a salt. It could be sodium chloride, like table salt. It's very tasty. Or it could be sodium iodide or potassium iodide. Any kind of ionic bond between group 1 and group 7 is going to be called a salt. All right, this is a model of an atom. Let's see if we can find out what atom we're looking at here. This model has a plus sign, a 0 sign, and a negative sign. Does anybody know what that plus sign represents? Protons, good job. And protons have a positive charge. They also have a mass of 1 AMU, or 1 atomic unit. So protons contribute to the mass of an atom. But protons are also how we identify an element, with the atomic number. So this one has 1, 2, 3, 4 protons. That means its atomic number is 4. I could also look back at my periodic table and find the number 4 right here. So I know that what I'm looking at is beryllium. So there's 2 different ways to find the atomic number. I could count the protons, or I could look on the periodic table. Now, what about these zeros? What do those represent? Neutrons. Do neutrons have a charge? No. Great job, you guys. No, neutrons don't have a charge, but they do also have 1 AMU. So they do contribute to the mass. And they're also found in the nucleus, in the center of the atom. That means that if I add the protons and the neutrons together, I'll get the atomic mass of the atom that I'm talking about, of the element that I'm talking about. So the atomic mass of beryllium would be 9, because I have 9 protons and neutrons. You can also find this by looking at the periodic table. The last thing that I have here is a little negative. What does the negative represent? Electrons. Yes, they have a negative charge, and they generally don't contribute very much to the mass. They have mass, but it is so small. They're so tiny that we don't count it. It's negligible, meaning we don't count it. But they do contribute to the volume, or how big the atom is, because they orbit out here. Now, electrons do orbit in certain energy levels, or certain orbitals. The very closest orbital only has space for 2 electrons. So that means that this is a full orbital, or a happy orbital. We want happy full orbitals to become the most stable. So for instance, hydrogen only has 1 electron. It could be stable with 2 electrons, because that would complete the first orbital. Or it could be stable with 0, no electrons. But something like beryllium here also has a second orbital, meaning it has 2 valence electrons. So it would probably be better if we lost 2 to reveal the first orbital, which is already full, rather than gaining 6. It would just be harder to gain 6. So the electrons are negative, and they're on the outside space. The protons and the neutrons are inside, and they contribute to the mass. Let's answer some questions. This is a different kind of model, but you can still see the nucleus and the orbitals. I want you to drag the charges to the correct labels on the atomic model. So you have a positive, negative, and a neutral charge right here. Just drag them over to where you think they belong. You have 30 seconds. Seconds. Yes. You can drag the icons. All right, what about now? All right. All right, 8 seconds. It's not working?
It's like it's working, but then we try to click a different one. It kind of.
Oh no. Okay. Always forgive my technology issues. I don't take blame for technology issues. I'm so sorry that didn't work out, but let's see what answers we did get. All right, no, don't laugh, don't laugh because this is actually this is okay. We'll talk about it. All right, so the first one is a plus sign. What does the plus sign represent?
Protons.
Protons, because they have a positive charge. Do they contribute to the mass?
Yes.
Yes, so we'll find them in the nucleus. So all the plus charges should be somewhere here in the nucleus. That is in the wrong spot, and that is in the wrong spot. So correct your answers. The plus sign or the protons are found in the nucleus, and they contribute to the atomic mass. The next thing we have is a little zero, a little green circle. It neither has a positive nor a negative charge, so we call it neutral. These are what kind of particles? Neutrons. Are they found in the center or the outside?
The center.
Yeah, they're found in the nucleus and they also contribute to the mass. So all the neutrons should be here and all the protons should be here. The last thing we have is a little negative sign. What does the negative sign represent? Electrons. And electrons do not contribute to the mass, so they are not found in the nucleus. Instead, they're found in the orbitals outside, and they contribute to the volume. So this is correct, this is correct, this is incorrect. So make sure to correct your answers. Let's look at the next question. This question says, what is the atomic number of this element? There's two different ways to find the atomic number. You have 30 seconds. Find the atomic number. You're supposed to find the atomic number. Give me a number. All right, your time is up. Let's see what kind of answers we got. Oh no, I only have 21 participants. I need 100% participation. So those last 4 people, you got to answer. If you're not sure, give me a number. I need 100% participation. We're going to talk about the answer in a second. We're going to talk about the answer in a second. All right, we've got 53 and we've got 127. Now, let's talk about where we got the numbers from. 53 is the correct answer. So if you put 53, that was awesome. 127 is not quite the right answer. I'm looking for the atomic number, meaning the identity of the ion, or I'm sorry, of the atom, which is iodine. If I look on the periodic table, the big number on the periodic table is the number of protons or the atomic number. That's 53. The other way I could find it is by looking at the model and seeing that I have 53 protons. So 53 was the correct answer. Now, what is the atomic mass? Tell me in 30 seconds, what is the atomic mass of iodine? What is the atomic mass? All right, 30 seconds is up. Let's see what answers we got. It's a little bit better engagement, but I still need those last couple people. If you're not participating, I'm going to look into the history, find out who you are, and I email you. You don't want me to point you out, so make sure that you're participating. All right, 126.9 or 127. Give yourselves a big round of applause. Yeah. Everybody got it correct. Remember, the mass is found in the nucleus. So one way we can find the atomic mass is by looking in the nucleus and adding together the protons and neutrons. The other way we could find the mass is by looking at the periodic table, and the little number on the periodic table is going to be the mass. In this case, it says 126.90447. That's a really weird number. Why is that number so weird? Because of the neutrons, okay, that's great. So some iodine has a mass of 127, but some has a mass of 126. So what they do, or what, whoever they are going to average together the known isotopes. That word iso means the same. Isotopes, it's the same element, iodine, but it has different number of neutrons. And this becomes very important in medicine because some isotopes will have more neutrons and some will have less neutrons, but they're always going to have the same number of protons because that's the identity of the element that we're talking about. A radioisotope is an isotope that undergoes radioactive decay. Now, there's different kinds of radioactive decay. Sometimes we're going to lose a neutron. Sometimes we'll lose a proton, but beta decay is one of the more common types in which we actually lose a neutron, but that neutron decays into a proton. So if tritium, which is a hydrogen with 2 neutrons, undergoes radioactive decay, one of these neutrons will actually turn into a proton. And then we no longer have hydrogen. We now have, let's go look at our periodic table. We now have helium. So that hydrogen would undergo beta decay into a helium. So that's just an extra little thing. All right. Radioactive atoms will release particles or electromagnetic energy from the nucleus because they're not stable. So hydrogen is most stable with a single proton. If we force a neutron on there, it's called deuterium. If we force 2 neutrons on there, it's called tritium. And these are non-stable, so they undergo radioactive decay. We can use this radioactive decay to do different things. We can measure it. It decays at a very specific rate. We can measure it, but we can also see it under radio imaging, and we can use it as a biological tag, meaning let's say your body uses a certain nutrient. We use this a lot in fMRI or functional MRIs, where you will be injected with a radio biological tag, and it can be seen in the MRI, lights up in the MRI. And so the doctor can view what's going on inside your biological processes. Where is that radio tag being used up? Which is really cool. So that's what we need to know about radioisotopes. But isotope just means the same element with a different number of neutrons. All right, a molecule. We talked about atoms. An atom would be a single atom of oxygen or a single atom of nitrogen. But that's not normally how we find things in the world, okay? They're not normally just pure out there in the world. There are some elements like gold you might just find in the ground pure. But most of the time, these atoms are going to make bonds. And when they make bonds, we now call them molecules. So a molecule is a particle consisting of 2 or more atoms held together by a chemical bond. In this case, I know that this is a covalent bond. We'll talk about covalent bonds in a second, but I know it's a covalent bond because we've drawn a line, and that represents a shared electron. So a covalent bond is here. This would be a molecule of caffeine. I like caffeine. I like coffee, so I used caffeine as my example. Okay. If you don't drink caffeine, good for you. Don't start. But if I have a bunch of things or a bunch of caffeine, then I'm going to call it a compound. It's a substance composed of two or more different elements kind of mixed together. So I could have a compound of caffeine like in a spoon, but I couldn't have a molecule of caffeine because it's too small. A molecule is one single one. And so this is the example that I used. All right. Chemical bonds. I already mentioned that there are different kinds of chemical bonds, but it's important to understand why we have chemical bonds. I already briefly described that atoms are most stable when they have a full valence shell. And that word valence means the outside electrons. And those outside electrons not only determine the properties of the element, but the reactivity of that element. So hydrogen here only has one electron, but it would be most stable with two because this inside orbital can carry two electrons. You can see here on oxygen, the inside orbital has two electrons. The second orbital can hold 8 electrons. It gets more and more funky as you get bigger and bigger, but the rule of thumb is 8 makes me happy, okay? The rule of 8 says that we want 8 outside electrons. So for something like carbon, carbon has 4 outside electrons or 4 valence electrons. That means it's looking to either gain 4 or lose 4 or share 4. So the most common thing that carbon is going to do is share 4 electrons so that it can have 8 valence electrons. Then we have something like oxygen. Oxygen has 6 outside electrons, meaning that it wants to gain or share 2 electrons so it can have happy 8 electrons. Sodium, however, you can see that sodium has a full shell in the second orbital, and then it only has 1 valence electron. Is sodium going to try to gain 7 electrons, or is it just going to try to lose 1? Which would be easier? Losing 1. So sodium is going to do a different kind of bond than carbon. Carbon is really going to share the electrons. Sodium is trying to get rid of electrons. So the most distant electrons, the outside electrons, are the ones that determine the reactivity and the properties. It would be really, really hard for a bond to reach into this middle. So you wouldn't want to use the inside electrons. We're going to use the outside electrons. And those outside electrons are called valence electrons or the valence shell. Chemically stable elements have 8 valence electrons. We talked about that already. But let's talk about sodium some more. Sodium does something called an ionic bond, meaning that it will gain or lose electrons instead of sharing them, okay? So sodium wants to lose a bond, and we know that sodium is in that first family. So sodium is really going to try to bond with something from the 7th family because chlorine, for instance, has 7 valence electrons. Is it easier for chlorine to gain 1 electron or to lose 7? Gain 1. Match made in heaven. Sodium is looking to lose 1. Chlorine is looking to gain 1. Now, sodium, we already talked about, is explosive in water. It's highly reactive. It will explode and catch on fire. Chlorine, however, is a poisonous gas. It kind of has a yellow-green haze to it, and it's poisonous. But when they exchange electrons, we no longer have sodium. We have a sodium ion. We have lost a negative electron. So is sodium ion going to be positive or negative? Positive. So we call it a cation. It's no longer explosive in water. Chlorine, a poisonous gas, it's going to gain a negative electron. So is it going to be a positive ion or a negative ion? Negative ion, we call it an anion. Now they're not sharing any electrons, so there's nothing really like connecting the two, but they stick very closely together, kind of like a positive magnet sticks to a negative magnet. A positive charge is going to stick to a negative charge very, very closely, and they create this crystalline structure of sodium, positive ion, and chlorine, negative ion. This is called an ionic bond. It's when an anion and a cation bind together. So it is a very strong kind of bond. but it can be disassociated, meaning, for instance, if I dissolved this salt in some water, I would then have separate sodium and chlorine ions. Is the sodium going to explode? No, because it already reacted. It's already lost its electron. So an ionic bond is always going to have a positive and a negative charge. Then, let's look at this. Iodine, same example as before, but now I want to know how many valence electrons are present. There's two different ways you can find it. You have 30 seconds. How many valence electrons are present in iodine? Seconds. How many valence electrons? There's two different ways to find the answer. 5 seconds. Get your answer locked in. All right, 22 out of 25 isn't bad, but I really want 25 out of 25, you guys. All right, let's look at our answer. We've got 7 and 53. Let's talk about where we got these numbers from. 53 is the atomic number. That's the number of protons, not the number of valence electrons. Remember, valence means the outside. So one way I can find this answer is by looking at the atomic model and counting 1, 2, 3, 4, 5, 6, 7 outside electrons. So the answer is 7. The other way I could find the answer is by looking at the periodic table and seeing that iodine is in family 7. If it's in family 7, it has 7 valence electrons, and on this image it actually tells you the shells. In the first shell, it has 2 electrons. In the second shell, it has 8 electrons. Then it gets a little funky. We got 18 and 18, but the outside one, which is the one that I care about, is 7. So 2 different ways to find the answer. All right, looking at this element, radon, is it chemically reactive? Yes or no? Is it chemically reactive? I want to see what you guys think. Is radon chemically reactive? 2 different ways to find the answer. 10 seconds. It's a yes or no question. I should have 25 out of 25 responses. 5 seconds. Click yes or no. Give it your best guess. Still 22 out of 25. 23 out of 25. Click A or B. All right. All right. Give yourselves a big round of applause. Okay, everybody said no, and the reason that we said no is because 8 is most stable, or according to our rule, usually 8 is most stable. And in this case, we can count the number of valence electrons, which is 8. So we're good. We're not very chemically reactive. Or you could look at the periodic table and see that radon is a noble gas, and noble gases are known to not be very reactive. That's actually how neon signs work, because we can jolt electricity through the gas and it won't blow up. It'll glow. That extra energy will come off as light. You can also look here and it says 8 is the valence, or the most outside shell. So we know that that's stable. All right, let's talk about a different kind of bond. This bond is called covalent bond. What does the word co mean? Together. Together. What does valent mean? Outside electron. So something that says covalent tells me that I'm sharing the outside electron. I like to say they're co-parenting. Covalent. They're sharing the outside electron. So in our example of hydrogen, as we know, only has 1 proton. So it only has 1 electron. Now, hydrogen would be happy losing that electron or gaining another electron. So hydrogen does this funny thing where it actually binds to another hydrogen atom, creating hydrogen gas, which is written as an H with a little bar connecting the other H. I know that this means they're sharing 1 electron. So now these electrons are going to orbit both hydrogen atoms. And so they are sharing the valence electrons, and they are both stable. Oxygen does the same thing. Oxygen has 6 valence electrons, meaning it would like to gain 2 electrons or create 2 covalent bonds. So that's exactly what it does. If the oxygen that we breathe actually isn't one atom by itself, it's oxygen gas, which is 2 oxygens covalently bonded together with a double covalent bond. They're sharing these electrons, and those electrons will orbit around both atoms. In these 2 cases, the orbits are even. They are evenly shared, but that's not always the case. In the case of methane, carbon and hydrogen are both about the same electronegativity, so they share the electrons evenly. Nothing is more negative than the other. But water is different. And water is not the only one that's different, but that's the example we're going to go over. Oxygen is extremely electronegative, meaning it really, really, really likes electrons. There's just something about oxygen. Oxygen is greedy with the electrons. So when oxygen covalently bonds with hydrogen, which is not very electronegative, it tends to hold on to those electrons. Now the electrons are still shared. It's not an ionic bond. It's still a covalent bond. But the electron spends a little bit more time around the oxygen than it does around the hydrogen. So we're sharing electrons, but we're spending a lot more time over here than we are over here. Electrons, what charge do electrons have? Negative. So that means the end that has oxygen is going to be a little bit more negative than the end that has the hydrogen. So we end up with a partial negative on one end of the molecule and a partial positive on the other end of the molecule. This is called a polar molecule. Just like Earth has a north pole and a south pole, these are magnetic poles. A polar molecule has a negative pole and a positive pole. If we look over here at methane, nothing is more positive or more negative than the other, so it is called nonpolar. This becomes really important in our bodies because polar things don't really like to mix with nonpolar things. Can you think of a nonpolar molecule that does not mix with water? Oil. Yeah, oil is a fat, and most of fats are going to be non-polar. They're long chains of carbon and hydrogen, so they don't really mix with water. So that's another reason why water is so cool, is because it has that slightly negative and that slightly positive side. So looking at this chart, look at these 3 molecules. I have a water molecule, a methane molecule, and a carbon dioxide molecule. Can you identify the polar molecule for me? Now can you see it? You should have a little star right here. Pull it to the molecule. You have 25 seconds. Which one is polar? That's why I don't like the phones. I know why you're using the phone, but you're just going to have to suffer and look at the board because sometimes the phones don't work as well as the laptops do. Okay, so let's look at what we said. All right, this is really, really great. So most people said that water is the polar molecule, which is great because I just said that water was a polar molecule right here. But water is the polar molecule. You see this little S-shaped symbol? That means partial. There's a partial charge of positive on the hydrogen end and a partial charge of negative on the oxygen end. This is a polar molecule. We know that methane is nonpolar because we just said methane was nonpolar. This is the same model or a different model of the same element or the same molecule. But we have nonpolar bonds. The confusing one is going to be carbon dioxide because carbon dioxide creates a polar bond, a polar covalent bond. We have oxygen, which is electronegative, and we have carbon, which is a little bit more neutral, but it ends up being electropositive when it's compared to the oxygen. But you also have to look at the shape of the molecule, because if we have a negative side on one end and a negative side on the other end, neither end is more negative than the other. So it is non-polar because it is not positive on one end and negative on the other end. Now, this is not a complete positive and a complete negative charge, which makes it really interesting when it does something called hydrogen bonding. Water undergoes something called hydrogen bonds. We call it hydrogen bonds because it most likely has to do with hydrogen. Since hydrogen is slightly positive and oxygen is slightly negative, when they come into close contact with each other, they create a brief connection. This is not as strong as an ionic bond because an ionic bond is a complete positive and a complete negative charge next to each other. It's just a partial positive and a partial negative charge. And so these bonds become very wibbly wobbly, kind of. They're easily broken, but they're also easily constructed. So they're easily made, easily broken, which is really, really convenient when we're talking about our biological processes, especially when we start talking about DNA. DNA is connected with hydrogen bonds because we need to unzip DNA and zip it back up very frequently in our biological processes. During replication of DNA and during transcription of DNA, we have to zip it and unzip it very frequently. And we don't want to expend a lot of energy doing that. So hydrogen bonds are really perfect. Anytime I have a partially positive next to a partially negative, it's going to make that brief connection, leading to a hydrogen bond. So hydrogen bonds are weaker than ionic bonds, but they're still an interesting kind of bond. This also leads to water being very sticky. You don't think of water as being sticky, but if I had 2 pieces of glass and I put a drop of water in between them, it would be really hard to pull that glass apart because of the hydrogen bonds. If you've ever put drops of water on top of a penny, it creates surface tension. That surface tension is because of the hydrogen bonds. Okay, so it not only sticks to other water molecules, it sticks to other things that are also electronegative. Water is super important for our body because it's the most abundant inorganic compound in our body. We use it throughout our body as the aqueous solution that dissolves other things. So if you need a salt in your body, like potassium and sodium, other ions in your body, other electrolytes in your body, they can't do their job unless they're dissolved in water. Our body is about 60% water, but this is just an estimate. I'm sure that different parts of your body have different proportions of water. For instance, your blood is very aqueous. It's liquid. So it's going to contain a lot more water than other parts of your body. It's important because it's the universal solvent. It can dissolve any other polar molecule. So for instance, those ions that we need for functioning, we need ions to function in our body. They have to be dissolved in water. So water is a universal solvent of our body. Water is also really important because it does not mix with non-polar substances. Y'all already told me that oil does not mix with water. Well, our cells have an outside layer made up of mostly fat. So that phospholipid bilayer, the membrane of our cells, are non-polar and they do not mix with water. That means that they're not going to break as soon as they become in contact with water, which is great because our bodies are made of water. So water is important because it can dissolve polar substances, but it cannot dissolve non-polar substances such as our cellular membrane. It's not going to dissolve our cells. It also has a high specific heat, meaning that it's going to absorb a lot of energy without causing damage. So if it helps regulate our body temperature. And hydrogen bonds become very important in different processes of our body, including capillary action, which is water just kind of goes through very small tubes very easily, and DNA. So I don't like that this says expands when freezes, which is true, but that's not important to our biological processes as it is important to some fish. But our DNA uses hydrogen bonds, which becomes very important. All right, inorganic compounds are also very important to our body, especially salt. Salt can dissociate or dissolve in water, but now our individual chlorine is no longer poisonous because, like we said, it's already exchanged its electrons, and sodium is no longer explosive because it's already exchanged its electron. But now this dissolved ion can conduct signals. The ions in our body are really, really important for nerve and impulse conduction. We see that in our brain and we see that in our muscles. So here is a diagram of a nerve cell or a brain cell. The longest one in your body is several feet long. It goes from your brainstem kind of to the mid part of your back. So these can conduct signals over very long periods, over long distances. And the way that this signal is conducted down the axon is with the use of ions, particularly sodium and potassium ions. So we have lots of sodium and lots of potassium in an aqueous solution. It wouldn't work if we didn't have water. And these ions kind of trade places and conduct an electrical signal down the axon. Your muscles undergo a similar process, and they also use calcium to conduct this signal. So your muscles and your brain is a really important example of where we need electrolytes in our body to conduct an electrical current. All right, let's switch gears entirely. We're no longer talking about water, kind of. Now we're going to talk about hydrogen. I told you that I'm a nerd for hydrogen. Hydrogen is super cool. Hydrogen does lots of different things. Hydrogen bonding is one thing that it does, but another thing that it does is exchange in acid-base reactions. So pH actually means power of hydrogen, or the relative concentration of hydrogen in a solution. If the concentration of hydrogen in the solution is really, really high, we call it an acid. If the concentration of hydrogen in a solution is really, really low, we call it a base or an alkaline. So why then are the small numbers acid and the big numbers base? Well, that's because it's shorthand. Power of hydrogen is shorthand for a logarithmic scale. So let's look at distilled water. Distilled water is neutral, meaning it is neither an acid nor a base. It's also a universal buffer. Another good reason for it to be in your body is because it's a universal buffer. It has a pH of 7, or if we're looking at the proportion of hydrogens inside of the water, it's 10 to the negative 7, meaning there's a decimal point and then 7 zeros before we get to the proportion of hydrogen in that water. It has equal number of hydrogens to hydroxyls. This column represents hydroxyls. What happens when we mix a proton or a hydrogen with a hydroxyl? We have 2 hydrogens and 1 oxygen. What is that? H2O. Water. So it makes sense that water is neutral because it has the same number of hydroxyls as hydrogens, or it has H2O. That also means that when an acid is mixed with a base, they become neutralized because the hydrogens mix with the hydroxyls or combine with the hydroxyls to make water. So water is one of the byproducts of mixing an acid and a base together. Now we have 10 to the negative 7. That's a really, really tiny number. As we go more acidic, we get more proportion of hydrogens. The most acidic is going to be 10 to the negative 1, 10 to the 0. If I put 10 to the negative 1 in my calculator, I'm going to get 0.1, right? Is that true? 0.1, or is it just 1? It's just 1.
It's 0.1.
It's 0.1. Okay. See, y'all, don't make me question myself. It's 0.1. 10 to the negative 1 is 0.1, meaning 10% hydrogens or 10% protons. That's a huge number of protons compared to down here, bleach has 10 to the negative 12. That means a decimal and then 12 zeros behind it. Very, very small number of protons. So an acid is considered a proton donor. Because it has so many protons, it's considered a proton donor. If it mixes with water or a base, these protons are going to be donated to create more water. Okay, these are the low numbers, 1 through 6. A base is known as a proton acceptor. It has a high number of hydroxyls, so it is going to steal protons to create water. These are our high numbers, 8 through 14. Humans, we really like to drink acids. We're like little acid lava monsters. We love acids. Juices, lemon juice, lemonade, coffee, all of those things are acids. Bases, however, are not so friendly to us. So we use them as household cleaners a lot because they're really good at reacting with fats. So any grease in your kitchen is going to be broken down by these. For instance, oven cleaner has a pH of 13.5, which is extremely, extremely basic. Bleach has a pH of 12. It will cut fats. Just a side note, never mix an ammonia cleaner with a bleach cleaner. If you're in your bathroom and you're spraying Windex on the mirror and you're spraying countertop cleaner on the sink and those gases mix together, it can release a chemical, mustard gas, or in different proportions, a chlorine gas. Very, very dangerous. So never, never mix ammonia cleaners with bleach cleaners. An ammonia cleaner is like Windex. Anything spot-free shine, floor cleaner tends to be ammonia-based, and then countertop cleaners tend to be like bleach-based. Don't mix bleach and ammonia. Evacuate the area and don't go back in because it can be very dangerous. But bases, soap is also basic. All right, let's look at when we mix an acid and a base together, they undergo something called a neutralization reaction. Neutralization reaction means that our acid is going to donate protons and our base is going to accept protons, resulting in water as one of our byproducts. The other byproduct will be some sort of salt, which is whatever's left over will bind together and create a salt. So the result of a neutralization reaction is going to be salt and water, and it should have a more neutral pH. So if our acid and our base are in equal proportions and they're equally distant from neutral, we will get a pH of 7 after a neutralization reaction. The universal buffer is going to be water because water can both accept and donate protons depending on what it's mixed with. So buffers are stabilizing the pH of a solution. All right, let's ask some questions or answer some questions. Looking at these substances, which one is more acidic? Now don't just guess. I want you to look at your chart. Remember, acids are higher up in the chart and bases are lower in the chart. Acids have more protons and bases have fewer protons. So you have 30 seconds. Which one is more acidic, tomato or lemon? Which one is more acidic, the tomato or the lemon? Okay, the left side is hydroxyls. It's basically the inverse of hydrogen. So here, a 10 to the 0 power of hydrogen is the same as saying 10 to the negative 14 hydroxyls. So when we look at alkaline is going to have a whole lot of hydroxyls, and acids are going to have a whole lot of hydrogens or protons. So you'll see that they're inverse. This down here is 10 to the 0. This up here is 10 to the 0. Okay, does that answer your question?
Yes, ma'am.
Great question. All right, I got 22 responses. Let's look at our answers. Great job. Give yourselves a round of applause. All right. Not to brag, but this morning's class didn't quite get that one. So great job, you guys. Now let's ask the same exact question in a little bit different way. It says, which substance has fewer protons? Pay attention. Which side has higher concentration of protons? Is it alkali or is it acid? Which one has fewer hydrogens or fewer protons? 30 seconds. Fewer protons. 20 seconds. a great observation. Look at the chart. Where is lemon juice and where is tomato juice? Let's see what our answer is. Ooh, I've only got 18 responses. Guys, I'm just asking you to drag a bubble. Drag that bubble. Which one do you think? Is it tomato or is it lemon? All right, about 50-50. Half of you said lemon, half of you said tomato. I'm looking for fewer protons or less acidic because acids have high concentrations of protons. So if I look at my chart, tomato juice has a pH of 4 and lemon juice has a pH of 2. That means lemons have way more protons. In fact, they have 100 times more because it's a logarithmic scale.
They're switching over.
Yeah, go ahead. Correct your answer. Yeah, correct your answer. When I'm looking at a pH of 4, I have 10 to the negative 4 concentration of protons. When I'm looking at a pH of 2, I have 10 to the negative 2 concentration of protons. Get off of my chart. I need to be able to see. All right, so that means in a logarithmic scale, that's a difference of 10 to the power of 2. 10 to the power of 2 is 100. Or an easier way to do that is just to say 5 to 4 is times 10, 4 to 3 is times 10, and 4 to 2 is times 100. So lemon juice actually has 100 times more protons than tomato juice. So if I'm looking for fewer protons, I'm looking for tomato juice. Now, looking at these examples, which substance is more basic or more alkaline? I have milk, which I keep in my refrigerator and give to my children to drink. And I have bleach, which I keep locked in a cabinet underneath my sink. Which one is more basic or more alkaline? Ah, there's no answer choices.
It's like a
Boom.
little dot.
All right. Keep answer on the computer. Don't say it out loud. 15 seconds. I only have 18 responses. I want 25 responses. Actually, I think that there's only 23 people here because when you log in and then log back out, it still counts you. So if you had to re-log in, it counted. All right, which one is more alkaline? The one that you drink or the one that you use to clean? Yeah, bleach. Come on, guys. I'm glad that y'all are having fun. I'm having fun too. But if you look at the pH scale, we can see milk right here has a pH of 6.5. So it's actually not even basic at all. It's actually an acid. It's a very weak acid. The reason why you might drink milk if you eat something spicy is because milk has a lot of fat in it and spiciness is an oil. It's called capsaicin. It's an oil, so it doesn't mix with water. So if you drink water when you drink something spicy, you're not going to get rid of that oil because oil and water doesn't mix. So most people will drink milk. It's not because milk is a base. Milk is a very weak acid. But what is a base is household bleach. It has a pH of 12, or it has 10 to the negative 12 protons. All right, let's answer another question. Which substance has more protons? 30 seconds. Which one has more protons? Oh, no dot. Which one has more protons? Seconds. Look at your scale. This is the column that's talking about protons. Which one has more protons? Is it milk or is it bleach? 2 seconds. All right, let's see. Ooh, almost 100%. So when I'm asking about protons, I'm asking about this column right here. And remember, 10 to the 0 power is a much larger number than 10 to the negative 14 power. So if I'm looking at milk, I'm looking at a pH of 6.5, meaning I have 10 to the negative 6.5 like protons, whereas bleach has 10 to the negative 12 protons. So if I'm looking for more protons, I'm looking for the more acidic milk. All right. What is the difference in pH? Now I'm looking for the difference in pH. Just give me a proportion. Is it 1 times difference? Is it 2 times difference? Is it 5 times different? Is it 10 times different? First, you're going to have to find the pH of water, which is right here, 7, 10 to the negative 7. Then you find the pH of coffee. pH of coffee is 5 or 10 to the negative 5. And then I want you to find the difference. You can just count 1, 2, and know that each one of those is a logarithmic scale or a multiple of 10. Or you can subtract 10 to the negative 7 from 10 to the negative 5. If you subtract 10 to the negative 7 from 10 to the negative 5, you get 10 to the second power. So, I think you know what, that's way too long. You should know the answer already. I'll give you about 15 more seconds. What is the difference in pH? I want to see what you guys say. I love listening to y'all help each other, and my favorite thing is when I hear you say, look at the scale. All right. I see that. Thank you for the suggestion. All right. Let's look at the answers that y'all gave me. Oh, no. What happened, guys? Oh, that is not the right answer. I didn't lie to you. All right. I said that a pH of 7 and the pH of 5. What I'm going to do is I'm going to count. 5 to 6 is times 10. 6 to 7 is times 10. What's 10 times 10? 100. So coffee has 100 times more protons than water, proportionally.
You can say it.
But look at the results again.
Because difference to us is subtract.
Okay.
So I was subtracting 7
No.
from 5.
Okay, let's clarify. This is why. Maybe I didn't do a good job clarifying. If you're looking at the pH scale, each rung is worth 10 times difference. So the difference between water and coffee is 100 times. The difference between water and tomato juice would be 1,000 times. But when I'm asking you to subtract, you can come over here to the proton scale and say 10 to the negative 7 minus 10 to the negative 5. Plug that into your calculator. It's going to say 10 to the 2. If I multiply 10 times 10, which is 10 to the 2, or 10 to the second power, I get 100, which becomes important when I'm asking you much larger numbers. When I'm asking you much larger numbers, that side becomes easier. For instance, you can say 10 to the negative 12 minus 10 to the negative 7. Instead of trying to count 10 times 10 times 10 times 10, I will get 10 to the 5 power, okay, or 10 to the 5th power. All right, so did we correct our answer? Yes, 100 times. Let's look at the next question. The next question says, what's the difference in pH or the difference in proportion of hydrogens between water and bleach? I'm going to give you 1 minute. Bleach has a pH of 12. Water has a pH of 7. So what's the difference in the proportion of protons? What's the difference in the proportion of protons? Remember, it's a logarithmic scale. 30 seconds. It's not 2 million. It's a wild number. Guys, not 2 million. 10 seconds, guys. Get your answer locked in. All right, let's see what we got. Surprise me, guys. Woo! Okay, it looks like,
I wonder what zero is.
yeah, it looks like most people were at 100,000, and then somebody put like 10 million or whatever number this is. Now, our correct answer is 100,000. Let's see how we got there. If I'm looking at a pH of 7, I'm going to say 10 times 10 times 10 times 10 times 10 to get to bleach. That's 5 zeros or 100,000. Or I can look at the logarithmic scale and say 10 to the negative 12 minus 10 to the negative 7, and I get 10 to the 5th power, which is 100,000, okay? Pay attention to the question and what it's asking you, because there will be a question on the quiz asking you to calculate the difference. It's never going to be 2. It's never going to be 5. It's going to be a multiple of 10. Yes, sir.
Oh, I should say yes, ma'am.
Oh, okay. Yeah, if you had a question, I wanted to answer it. All right, that's it for us. Now, we're not going to do the discussion because we generally don't have enough time to do the discussion. So it's just a dead link right now. Actually, you could link to it, but we're not going to do it just because we don't have time. But looking at this page, the first thing I want to talk about is the chapter laboratory write-up. Whether you're absent or not, you will still click on this and print it out. Where do you bring this printout? To lab tomorrow. Don't come to lab without this printout. Where is lab going to be? Across the street. So make sure to bring this to lab. If you're absent for any reason, you are still responsible for the lab quiz. Still print it out, but what you're going to do is you're going to scan the QR code and follow the instructions in the video. It's not the best experience, but it works. Then I want you to do the chapter quiz. When is the chapter quiz due?
Friday at 5.
Friday at 5 p.m. The reason it's due at 5 p.m. is because I don't want you taking it at midnight on Sunday night and then stress out and something goes wrong and I'm not available. So I want you to take it before Friday at 5 p.m. It's open, available to you. Take it the first time you came to class, you took notes, you know what you're talking about. Take that quiz. It's a really good indication of how you'll do on the exam because it's the exact same questions as the exam. So if you make a 90 or a 100, move on. You already know the stuff. You don't need to study anymore. What happens if you make like a 20 or a 30? Review. And the places where you can review are either the chapter homework. The chapter homework can be turned in for extra credit after the first exam. What you'll do is you'll make a copy of it by clicking this link. You'll watch the videos and complete the activities. If you ever need help with it, let me know. Also, your SI leader should have access to this homework and they can help you with it as well. If you don't like doing the homework, I have other study materials for you, including the textbook, and this will link directly to the chapter that we're working on. And the Quizlet. This is flashcards or vocabulary cards. Now, in my opinion, the Quizlet is a little bit harder than the actual test. So if you're studying the Quizlet, you're pretty well prepared because these are actually more difficult. Then this is a vocabulary booklet. It's a game that you can play on your own. This is also what we will go over with our review. When we get the opportunity to review, that's what we will use. The other study material that I wanted to talk to you about is located in Blackboard. So if you're studying Unit 1, you click on Unit 1 in Blackboard, you'll see the unit quizzes. On the top of the unit quizzes, you'll see the unit lesson. This is the lesson for all 3 quizzes. It's up here, let it load. You can press start here, and then you will have access to all the PowerPoints. So if you click on 1.1, you will get to the PowerPoint that we went over today, and you can review it a little bit more if that's what you want to review. Or you can click 1.1 practice. The 1.1 practice is linked to this something called quizzes. Quizzes is an adaptive release quiz, meaning if you get the answers right, you don't have to answer as many questions. But if you get the answers wrong, it'll give you more similar questions. So it's a really great resource to practice without it affecting your grade because you only get 2 chances to take the Blackboard quiz, okay? Don't take those Blackboard quizzes without studying, but you can take this one. And it's the exact same question. So it's a preview of what might be in the quiz. So this is another really great resource for you to study. All right, does anybody have any questions? Yes.
So with our quizzes, it's on the respondents monitor and we can't use any notes. It's just based on.
Right, that is a great question. You can use your notes in lab, but not in lecture. In lecture, you can't use any notes. It's under Respondus Monitor. If you don't want to use Respondus Monitor, then you have to make an appointment with the Student Center. If you do have Respondus on your computers, you can take it at home anytime you want to, but you cannot use notes. In lab, it's a little bit different. In lab, you are allowed to use your notes. So it's an open quiz. So everybody should make 100% on the lab quizzes because the questions come directly from the lab notes. Okay, that was a great question. Any other questions? What's up?
You talked about for some sections of the test, you have to use a razor notes.
That's in lab, yes. So I don't think that I have Respondus turned on for the lab quizzes, but the lab practicals, I do have Respondus turned on. And in that case, you can still use your notes, but at the very end of the lab practical, it'll ask you to present your notes, and that's when you'll do that. Yes.
So how will it detect us? So if we look down and look at our notes, will it detect us as cheating?
No, because it's different settings.
Oh.
Yeah, it's different settings. Yes, sir.
Is it by Friday, right?
Yes, always Friday at 5. The due dates are always Friday at 5 for lab and lecture. Yes.
So can I do it tonight?
You can do it tonight if you want to. Don't take the lab quiz tonight because don't take the lab quiz until you do the lab handout. But you can take the lecture quiz tonight. If you do really well, you're good to go. If you do really poorly, that gives you a few days to go over the materials again before you retake it. All right. Y'all have a great week, and I will see you tomorrow.
See you tomorrow. Can we dissect the cat?